Alrighty, in the last video we talked about how to graph sine and cosine of theta, and now we're going to talk about how to graph tangent of theta. Now, as I said at the end of the last video, tangent itself does not show up directly in the unit circle. Now, the unit circle has x-coordinate of cosine of theta and a y-coordinate of sine of theta. So where exactly does tangent show up? Well, to see this, let's actually look at one of these triangles. So let's just take a look at this first one here, the 30-degree triangle right there. So remember that right here, and this is in the way for some reason, I don't know why that is. Sorry about that. Okay, so here is a 30-degree angle. Right there, that is our theta. If we remember, well actually let's also fill out our coordinates. So our x side is root 3 over 2, and our vertical side is 1/2. Again, this is just the x, y pieces right there. And so, well, tangent of theta, if we remember, is equal to opposite over adjacent. And so tangent of 30 is equal to 1/2 divided by root 3 over 2. And if I simplified this, this would simply be 1 over root 3. Now, here's the thing. I actually hardly ever remember tangent of an angle. And here's why. What is this 1/2 and what is this root 3 over 2? If we think back to where those came from, root 3 over 2 right here is actually cosine of 30 degrees. And the height, this 1/2, is actually sine of 30 degrees. So in actuality, tangent of theta, or sorry, let's use this a specific example. Tangent of 30 degrees is actually equal to sine of 30 degrees divided by cosine of 30 degrees. In general, then, tangent is actually equal to sine of the angle divided by the cosine of the angle, and this is always true. And we can just see it from this picture. Notice that this is also the slope, as we said before. So if this right triangle you can imagine as a slope triangle, this is also equal to the slope. Because opposite over adjacent is really rise over run. And so now we can just imagine what all the slopes are at each of the angles. So let's look. At 0 degrees, well, sine is, well, actually, sorry. At 0 degrees, our angle is at 0, so our ray is flat. And therefore, if a line is flat, its slope is 0. And this also checks out because at 0 degrees, let's see, tangent of 0 degrees would equal sine of 0 divided by cosine 0, which would simply be 0 over 1, which is 0. So that checks out. I'm going to only plug in one more, and that's not at 45 degrees. And the reason I picked 45 degrees is, well, it's one that I actually remember, and the reason being is at 45 degrees, I know that sine and cosine are equal right here. And so if they're equal, then sine over cosine is going to equal 1. It's going to equal 1 right there. Oh, sorry, 1. Now we can see that the slope is getting steeper, which makes sense. We can see that right here. If I pull out my ruler and just center it on the origin here, it starts off flat, and then of course as I go around, then my slope gets bigger and bigger, positive that is, more and more positive, until what happens? Well, when I get to 90 degrees, my slope, if we think about what our slope was, or think back to Algebra 1, how we name the slope when the line is vertical, we'd say it's undefined. And so in actuality, you can't calculate tangent of 90 degrees. And so 90 degrees is actually not in the domain of this function. I cannot take tangent of 90 degrees. If we think about it in terms of sine and cosine, remember, tangent of 90 degrees is equal to sine of 90 divided by cosine of 90, which would be 1 over 0, which we don't want to do. Not yet, anyway. And so 90 is not in our domain. And so what's happening is that my graph is getting steeper and steeper, or sorry, my line or my ray around the unit circle is of course getting steeper and steeper. And so that's going to look like this, and it's going to go up and up and up. Now what happens if I pass 90 degrees? Well, if I pass 90 degrees, as soon as I just go a tiny bit more, this slope right here, it exists, right? It's some really, really steep slope, but it is negative. And so our graph is going to look like this. It's going to start off really negative, or continue from a really negative point until when? Well, at 135 degrees, again, this one has a reference angle of 45, and so that slope is also 1, except now it's negative 1. And so at 135, we're at negative 1, so I kind of messed that up there. It's going to look something like this. Let's try to make it a little bit better. Come on. And then at 180 degrees, it's once again flat. And so it's going to look something like this. And then it's going to turn up. Oops. Once we are at 180 degrees, come on. Once we pass 180 degrees, it's now suddenly positive again. And then starts increasing steeper and steeper positive. And so this now goes up like so. Until, once again, your next angle that next problem you're going to run to is once you have a vertical line again, which is at 270 degrees. And so 270 is also not in our domain of this function. And so this graph just looks like so. Notice the first chunk right here in blue, that first chunk doesn't have a back end, if you will. But if we imagine that we started off at 0, and instead of going counterclockwise, we go clockwise to go backwards and count the negative angles, notice we have positive slopes, negative slopes that become more and more negative until we get to negative 90 degrees. So once again, negative 90 degrees, negative 90 degrees would also not be in our domain, because again, that would be an undefined slope. So this graph will look like so. And this would keep going. So notice here, what is the period now? In the past, it has always been, well, sine and cosine were both 360 degrees. So I can see maybe this would be a period of 360 degrees. But notice, do I actually need that entire 360 degrees to get the entire picture of the graph? Not really, because this piece and this piece, and the two green pieces, are exactly the same. And so this is enough for one period. And so the period is actually equal to 100, it's only equal to 180 degrees. And let's just fill in our domain and range. So let's actually copy that here. The period equals 180 degrees. Our domain, so this is interesting, what angles can we not take the tangent of? This would involve any angles where the slope on our unit circle, the slope of the ray here as we rotate it is vertical. So that happens at any multiple of, well, not any multiple, at 90 degrees and at 270 degrees. And also any other angle that comes up like that. So what I mean by that is not only is it 90 degrees, but so did negative 90 and 270. And so if we just keep bouncing back and forth between these, we're always adding 180 degrees. There's 180 degrees between 90 and 270. And so the way we would denote this is I would say that theta, oops, that was weird, theta cannot equal, right? Sometimes for a domain, it's easier to just say what x cannot be, or what the input cannot be. Theta cannot equal 90 degrees plus 180n. And this is implied that n equals an integer. So this was like saying 90 plus, well, 0, then 90 plus 180, 90 plus 360, and also backwards, right? 90 minus 180, 90 minus 360, etc., etc. So this covers all those bases. And our range, well, since this is the slope, we can have a super steep slope, super steep positive slope, or a super steep negative slope. And so actually the range is all real numbers. It could be any slope. Tangent can take on any value. So hopefully that made sense as to how we can use the unit circle, even though it doesn't have tangent, even though it doesn't have tangent on it directly, we can still use the unit circle to calculate tangent and thus graph it.